Hola, hi, this is Al Nozal, your statistics instructor. Let's get to work. In this short video, we will talk about matrix determinants. We are interested in the determinant of a matrix A because that can help us establish whether or not the inverse of the matrix A exists. We care about inverse matrices because we can use them to solve systems of linear equations. And matrix inversion is a key component of many statistical analyses, such as linear regression. Before we continue talking about how you can compute a determinant of a matrix, first let me say that the determinant quantifies the variability of a matrix. If we think of a matrix as a box, the determinant represents the volume of that box. Okay? We'll see an example in a moment. Well, now let's move on. Let us start talking about a simple example. 2x2 matrix A. Here's the example that I had in mind. Okay, I would like to remember how we compute the determinant for a simple matrix like this one, a 2x2 matrix. Okay, notation. We are going to be using a notation similar to the absolute value for the determinant. Okay. Now, let me remind you that to find the determinant of a 2x2 matrix, all you have to do is multiply these two elements located on this diagonal, 5 times 4 in this case, minus these two elements located on the other diagonal, 2 times 3. So in this case, the determinant turns out to be 14. And again, the absolute value of the determinant is a measure of variability when you think about these guys, these columns, as column vectors. Okay, next let's find out how we can compute determinants using R. Let's launch R. Now remember what we did when we discussed the concepts of matrix addition and matrix multiplication. The first step, if you wanted to carry out those operations using matrices and R, was defining your matrices. Well, it's going to be the same in this case. First, we need to define our matrix A, and we are going to be doing it in the same way we did it back then, using these special commands, matrix and C, that stands for concatenate. So in this case, the vector that we want, the two column vectors that we want, are 5, 3 and 2, 4. Remember that R reads vectors as column vectors. The additional parameters that we need to define our matrix are the dimensions, meaning the number of rows and the number of columns. In this case, 2 rows, 2 columns. Okay, let's type the name of the object we just created, A, and it is the matrix we are interested in. To find the determinant using R, the special command is det, the first three letters of the word determinant. Okay, 14. So we did it correctly. Nice. Before we move on, let's talk about that geometric interpretation that I was mentioning. Okay? So, to do so, I prepared a graph for you. Okay? Take a look at that graph. What I would like you to do is to find the area of the region defined by the red arrows or column vectors and the red dashed lines. But first, let me just underline the way we're thinking about these arrows. If we go back to the way we defined our matrix A, first column vector 5, 3, second one 2, 4, right? 5, 3, 2, 4. We're thinking about those guys as column vectors. Now, as I was saying, let's try and find the area of the region defined by these two red arrows and these two dashed lines, red dashed lines. Okay, an easier way of finding that would be, hey, how about we find the area of that square first, and then we remove the areas of triangles C, B, D, F and rectangles A and E. That would be easy, right? So that's what we're going to do. Okay, so the area of our region of interest, area of region of interest. Let's go back to our graph. So first, the area of that rectangle, 7 times 7. 7 times 7, that's going to be 49. Minus, we said we're going to remove the areas of these two rectangles, right? So note that the base is 2, the height is 3 for this one, base 2, height 3. So 2 times 3, 6, 2 times 3, 6 as well. So let me do that. So 49 minus 6 minus 6. Those are the areas of those two rectangles, A and E. Now let's remove the areas of these guys. For instance, C and F. So it would be base 5, height 3. So 5 times 3, 15, divided by 2, because it's a triangle. Note that in this case, base, it's upside down, but the base is 5, and the height is 3. So 5 times 3, 15, divided by 2 for C and F. Okay? So we have minus 15 divided by 2 minus 15 divided by 2. Minus 2 more triangles and we're done. B and D. So note that the base of this guy would be 4, right? The height 2. So 4 times 2 divided by 2, because it's a triangle. That would be the area of D. But then we go to B, and guess what? Height, the same, 2. Base, the same, 4. 4 times 2 divided by 2. So we end up with a 4 in both cases, for D and B. So we have 4 minus 4. So we have 49 minus 12. Since we have 15 divided by 2 minus 15 divided by 2, that happens to be the same as minus 15. We combine these two guys, minus 8. So now we have 49 minus 27 minus 8. That's 49 minus 35, which happens to be 14. Nice! The same result that we obtained before. Okay? So in the case of higher dimensions, right, and for instance in R3, we could instead of having a flat, something flat, a surface, we would be finding volumes. The determinant would be the volume of the box defined by the vectors of interest. Anyway, what I want you to remember is that the determinant is a measure of variability, the absolute value of the determinant. Okay? Okay. Let's move on. What I would like to do is see how we can use determinants to solve systems of linear equations. Well, it turns out that there's an approach called Cramer's rule. Cramer's rule applies only when the number of equations equals the number of unknowns. That rule is going to help us solve systems of linear equations using determinants, but only under those circumstances when the number of equations equals the number of unknowns. Okay? As usual, we will use an example to illustrate how that works. Okay? Let me find the example that I want to discuss with you. So, Cramer's rule example. A simple system of two linear equations that looks like this. First equation, 5 times B1 B1 plus 7 times B2 2 equals minus 11. That's the first one. Second one, 8 times B1 plus 4 times B2. That equals 4. Okay? That's our system of linear equations that we want to solve using Cramer's rule. So, first step, and this is going to be useful in the near future when we talk about using matrix operations and matrix representations for linear regression. Okay, so anyway, going back to this. First, let's try and re-express the equations in matrix form. What we could do is let's define, well, let's write the matrix defined by these coefficients, the coefficients for B1 and B2. So we would have that kind of matrix. Since we now have very fresh in our mind how the multiplication of matrices works, well, then if we want to have something equivalent to what we had above, this is going to work. Right? So we have, in this case, we have a 2 by 2 matrix, and this is a 2 by 1 vector. So they are conformable, and if you do first row times this column, this is going to yield 5 times B1 plus 7 times B2, right? And we want that to be equal to minus 11. This one, 8 times B1 plus 4 times B2 equals 4. Nice. So just using our operations, matrix multiplication, we were able to re-express that system of two linear equations in terms of matrices. Okay. So we would like to solve that system of linear equations using this particular rule, Cramer's rule. How we go about that? Well, first we're going to define something called delta, a capital Greek D, and that represents the determinant of the system. We know that the notation that we're going to be using for determinants is something similar to the absolute value. We're going to be using this notation, a capital Greek D, a delta. And delta is defined as just this matrix. So the determinant we know is going to be 5 times 4 minus 7 times 8, which equals minus 36. Okay? Okay. Next, we're going to define another matrix, delta sub B1. Okay, let me write it down here. Delta sub B1. Okay. And that guy is going to be formed by the following columns. We're going to replace the first column of the matrix delta, this guy, we're going to replace 5, 8 by minus 11, 4. And then we are going to compute the determinant of that matrix. Okay? So for this guy, let me do it step by step, so you remember exactly what we said we're doing. So minus 11 times 4 minus 7 times 4, right? Which happens to be minus 44 minus 28, and that gives you minus 72 as a result. Okay? Let's do something similar for delta B2. Now that's going to be the next quantity. Oops. So in that case, instead of substituting the first column, we're going to substitute the second column vector by this column vector. Okay? So in that case, what we end up with would be 5 times 4 minus 11, well, minus 11 times 8. Makes sense because we're going to be replacing this guy with this guy. Okay, let me write it down here. So 5 times 4, 5 times 4 minus 11 times 8. And if you do the math, that happens to be 108. Finally, because our ultimate goal is finding the solution for, or a solution for this system of linear equations, right? So B1 is going to be defined as follows. It's going to be the result of oops, sorry, not what I wanted to do here. Here's where I want to do that. It's going to be the result of dividing the determinant of B1 divided by the determinant of the system delta. Okay, so in that case it's going to be minus 72 divided by minus 36, which was the determinant of the system. Remember, here we are, right? Okay, so that happens to be 2. We do something similar with B2. Is going to be the determinant delta B2 divided by the determinant of the system. Okay, so it's going to be 108 divided by minus 36, so 108 divided by minus 36, and that happens to be exactly minus 3. Okay, Nice. So finding B1 and B2 like this using determinants is what is referred to as Cramer's rule. Okay? Now, I would like you to note something. Notice that if the determinant of delta, right, is 0, then we can't use Cramer's rule. But a determinant of 0 like that is revealing a linear dependence in the matrix. So what that means is that one or more of the vectors is a linear combination of another vector. Okay? Make sense? For instance, I think that I have an example here. Let me show it to you. I think if I remember correctly, slide 30. Yeah. So see, for instance, clearly if you multiply this column vector 5, 2 by 2, 2 times 5 gives you 10, 2 times 2 gives you 4. So this guy is a linear combination. This guy is a linear combination of this guy, or you could think about it the other way around, right? If you divide this by 2, you get this guy. So anyway, these two column vectors are linearly dependent, and that is revealed by the determinant. You end up with a determinant of 0. Make sense? Okay. And when you have a determinant of 0 for a matrix, what you say is that that matrix is a singular matrix. Okay, let's stop here. But before I let you go, let's summarize what we did. We talked about determinants, how they are computed, about their geometrical representation, and how they can be used to find the solution of systems of linear equations with something important, something to bear in mind here, with the same number of equations and unknowns, right? And the way that we found these solutions is called Cramer's rule. Well, that's it. Please take care and keep working hard. See you next time. Bye.